differ. So we cut device cross-sectionally. Then this is the cavity. We have a big mass here. So this is a membrane, a thin film membrane. And the black one is the piezo actuators. Then we have piezo resistors. Then PZT actuators. We supply voltage. It will bend. So you just imagine, if you will supply voltage to the PZT actuator, this one will bend. Piezo actuator will bend. And we have piezo resistors near the fixed side of the device. And this is the piezo resistor equation. Delta R divided by R equal to pi times sigma. Marcel, could you read the first point?
For p-type resistors aligned along the 110 direction, the piezoelectric coefficients in the longitudinal and transverse directions are almost equal in magnitude, but with opposite sign.
Yes, we have derived the equation for pi L and pi T along 110 direction several months ago. We have proved pi L and pi T almost the same magnitude with different sign. One is plus, the other one is minus. Then, Ami, could you read the second point?
The resistors are connected to form a 4-Wheatstone bridge, which ensures temperature compensation.
Thank you. We have half Wheatstone. We have full Wheatstone. For the half Wheatstone, we just have one R. We have one delta R, and the other three are fixed. But for full Wheatstone bridge, we have 4 R. These 4 piezo resistors are variables. They can change. And the thing is, you have 4 R. If there's the temperature increase, all the R values are increased together. So it is temperature isolation. So we can isolate temperature effects if we use Wheatstone bridge device. Okay, next page. Kyler, could you read the first point?
They choose to leave the resistors unconnected so that each resistor could be measured independently.
Yes, for MEMS, when we do research, we want to create a device we can measure the R values. So when you fabricate your device, you need to have, device 1 with all are connected as a Wheatstone bridge. But you need to have another device, and the 4 R's are not connected. And this way, you can use your multimeter to measure the resistance individually. So always think about experiment measurement. It's not just to one device work. We need to think, we need to calculate each component. So, Martin, why do we want to calculate each component?
In a combiner, we cannot determine each value. So that's why we need, in can,
So
in assembly we can just confirm the effect of the all.
if we have a group project, and in this group we have 4 members, and in the end we have group report, but I don't know which student contribute the most to the final project report. So better I could divide the big project into 4
Parts.
components, and let each one be in charge of one part, then I could know which one can work better than the others. What? Could you read the second point?
Each piezoresistor is connected in a simple voltage divider to a 5 voltage.
Okay, it's just their design. So they divide the 4 devices into 4 individual components, and each piezoresistor is connected to the supply voltage, power supply by volt. Okay, next one. Okay, this is, they got 4 piezoresistors, PR1, PR2, PR3, PR4. And because they separate them, so they could measure their delta R change individually. And this is the displacement of the center of the membrane, and micrometer scale. And the Y coordinate represents the delta R change. Then PR, like 2 of them follow, one goes down and the other 2 goes up. So when we design the full Wheatstone bridge 2, so you can imagine, so this one and this one goes up, this one and this one goes down. So yes, they could do this. Next page. Okay. Another application of piezo resistors. You can imagine we have a gripper. The 2 gripper grip the cantilevers. Young man, somehow just look at me, and when I say next, so otherwise, when I say which one is the gripper, which one is cantilevers, A, B, C, you may not be able to see my fingers if you just look at the screen. Once I sit there, please. I will control. I will. Please, please. Yeah, please. See, we have the gripper. So we control the gripper to grip the cantilevers. And you can think cantilever B is the reference device. It won't deform. So R value of B stays the same. But the A is deformed by the gripper. So RA will be varied. See, this is a Wheatstone bridge. So RA will be varied for this guy, John 2014 work. So vary A and cantilever B resistance stays the same. Then V out supply voltage ground here. We measure V out of these 2 points. Dick, am I right? BPAP. Okay, BPAP, could you read the first point?
Cantilevers A and C with SU8 structural layer and a copper piezoresistor strain gas relay.
Okay, thank you. So copper, also, all materials has piezo properties, all everyone, even our skin, everything. We apply force. If you measure the voltage, you could measure some voltage potential difference. but because this is too small, so we cannot measure it. But for piezo materials, the delta R or delta V might be large, so you could measure it. Okay, so copper also is a piezo-resistive material. So they use copper for the piezo-resistivity. Okay, could you read the second point?
To reduce the noise and between two resistors R1 and R2, candidate A and another simple candidate B placed near candidate A as the reverse sensor are connected, forming a Houston bridge.
Okay, see. So if this one is the MEMS resistor, and this one is the reference one, and R1 and R2, we could think they are also fixed. They won't change. So this is a Houston bridge. Okay, next page. I'll do. And because the bead we have copper, and copper, the bead we have copper on top, and we have SU8 as a structural layer. So we have two material for the bead. E1 and E2 are the Young's modulus of this. One is for copper, one is for SU8. So see, delta R divided by R equal to pi sigma, and the sigma equal to Young's modulus times strength. So we can for layer structure, cantilever bead, this is copper. The yellow part is the copper. Goes this serpentine formation, and the light blue part represents the SU8 structural layer. So copper on top of the SU8. We have the dimensions marked on this schematic figure. So we can derive, you apply a force F, then we calculate the strain, then do the integration, go through those mathematical processes. In the end, we can get these beautiful equations. See, almost all journal papers have some equations. So just, this is typical, without mess, without papers. You are a PhD student, right?
Masters.
You are master student? Oh, you look like a PhD. It is a compliment. Okay, so for electrical engineers, they need to derive the circuit equations. For mechanical engineers, they need to derive the mechanics equations in order to make you look good. Frank, am I right?
Yeah.
Equations. Okay, this is the fabrication process. So we use the silicon wafer, and on top of silicon wafer, we have oxide, 1 micron oxide. Then we just coat this undercoat material because SU8. Okay, let me ask Frank, why do we need this undercoat layer in this fabrication process? Because, okay, let me explain the fabrication process. So on top of undercoat, we can pattern SU8, the polymer. Then we just use, say, spatter. We can spatter copper, the yellow, all over the wafer. Then after that, we can coat BP212. is the polymer, 2 micron. Then we could pattern. We can remove the BP212 here. So only this BP212 only cover the copper here and copper here. So because BP212 protect the copper, so we remove the BP212 here, then we use the copper agent to remove the copper here. So we are left with this BP212 copper. Then we just put the wafer inside the developer to remove this BP212. So this is then after that, we just this is silicon dioxide. So we could use the agent to remove so let's say we can use the agent to remove honeycomb to separate this SU8 copper material from this silicon wafer. Okay, this is the fabrication steps. Frank, what's the purpose of honeycomb? Why do we use?
I think maybe we need the only code to protect the silicon wafers.
Protection?
Yes.
Can you think about? So on your left hand side, what's your name? Steven. What's the purpose? What do you think? Why do we use this layer honeycomb in this fabrication process?
Because the silicon outside will oxidation.
I could think of 2 reasons. The first one could be because SU8 is not easy to adhere on the oxide. So we need a middle layer. This middle layer easy to attach to silicon dioxide. Also easy for SU8 to stay on top of it. So this is one reason. It's a adhering layer, the middle layer, If say I like bebop don't like me, but bebop likes Lai. So I could ask Lai, could we go out to dinner? If I ask bebop, he wouldn't go out with me. But if I go ask Lai to ask bebop may say yes. So we have 3 people to have dinner together. So Lai is the honeycomb layer because Lai likes me. Lai likes bebop. So Lai is the honeycomb layer. Okay, that might be one reason. Another reason here, because honeycomb we can use some agent to dissolve honeycomb. Chemical reaction. We can use chemical agent to dissolve this honeycomb. Then this one and this one can be separated. That's another reason. It's a sacrificial layer. Sacrificial means this layer could be sacrificed in order to release this cantilever bit. Okay, 2 possible reasons. Purposes for honeycomb. But if you read the paper, you may know, which one is the real reason, which one is the better reason for us to use honeycomb. SU8 is a very difficult resist to work with. It's a negative resist. So negative resist is has anyone used SU8 in your experiment? Negative resist. Okay, good. No. Okay, so this is the ON photo. So this is the cantilever bead. We have the copper, the meandering copper goes in and goes out. So this is the scale bar for any micro device. Remember, put the scale bar on your ON photo in order to let people know the scale of your device. Okay. Ethan. Do you have Ethan? Ethan, did you read this?
The resist of the copper general resistance trend stage is about 0.7 k ohm at 25.
Yes, around 0.7 k ohm, 700 ohm. And it's important, this is room temperature, because resistance is a function of temperature. Different temperature, different resistance. Okay. Frank, what are the two possible reasons, purposes of the Omni code?
So for the unicode, the first one reason is to kind of the appearance, and the second reason is that the like the
Steven, what is the second reason? Possible second reason? Yes, sacrificial layer. Be professional. You should say sacrificial. Sacrificial layer. Okay, so yeah, this is the measurement. So we could skip this one. Okay, MATLAB. So the MATLAB we have dashed line, and we have dotted line. We have different colors, and we have the legend. So MATLAB is a very good software. Almost a lot of journal papers, you can see MATLAB everywhere. MATLAB is the ghost. They are everywhere in the journal papers. So that's why I promote the use of MATLAB. So I hope you can be familiar with. But you can use TechPlot, another plotting software. And there are a lot of other softwares. MATLAB is one of them, but a good one to use. You could see this micro, see the micros, yeah, the Greek number. Okay, good. Then I will ask Ethan, Steven, Frank. Sorry, your name. Leo. Did you read the first point?
With a strong contact between the bend end of the bar, spring and electric the area of the sensor, the capability of the contact resistance are smaller than 0.5% of the perovskite strength grade resistance.
Okay, good. Thank you. See, when we do the measurement, this is the micro device. They need to use the probe station to push this cantilever, push down to deform the cantilever. And see, okay, this is the experimental setup, the microscope, the testing device. And so we use the first photo. This is the first enlarged of this area, but this is still not easy to look. So we enlarge this small area, this one to this one, so you can see the micro device, tiny square here. So use the one probe station, one probe to push down this cantilever. And this one, this one, this one. And always scale bar to let people know the scale of your device. So you could have a theory. In order to measure the resistance, you need one wire connection and one wire connection. But two wire goes in. Wire has resistance. If the wire resistance is much larger than the piezo resistance, it doesn't make sense. And also, we have pad. Between pad and the probe, we have contact resistance. The contact resistance might be very large, much larger than the resistance. So it doesn't make sense for the result is useless. So we need to use a package. We need to use the, say, a good connector to decrease the contact resistance or the wire resistance. They say they have very strong contact between the probe and the pad. So they could measure the piezo resistance because they say the contact resistance is less than 0.5% of the piezo resistance. So they said, fine, it can work in their case. And in their experiment, they use electronic builders. Electronic builders is a scale to measure weight. We have a scale to measure human weight, a large scale. We have small scale, precision scale to measure the tiny object weight. But in this case, if you have probe, and we have a low cell at the end of the probe, so we push the probe to the micro cantilever. The low cell here will measure the downward force. But they use the electronic builders to do that. Okay, so the sensitivity voltage divided by Newton, 0.1 volt divided by Newton. So for any meaningful result, your output voltage should be in the millivolt range. Or is less than millivolt. It's too small to measure because we have noise, we have a lot of uncertainties, electronic noise, thermal noise, even vibration noise. So not easy to do this measurement. Okay, another topic. What time is it? We have another device. It's a resonator, vibration. And see, for this beat, this is a beat. We have support 1, support 2, support 3, support 4. We have 4 anchors. So this beat, this is free end. So this beat will bend. So for any journal publications, you need to have a beautiful figure. So this is good way for MEMS researchers, for guys doing MEMS. This is transparent. You could see the poly inside. You could see metal layers. And use different colors. So this is light blue, this is brown, this is ocean blue. So when you present your result, so this one is very clear. So you have the contact. You have the, this is the solenoid or inductor. This is ground, and this is output port. And we have a coupling capacitor. And this one is the input port. Then we have this inductor, and this is supply voltage, VD, and ID is a DC current. So, and port 2. For DC, so we could say DC signal goes in and goes through this piezoresistor, goes out. For DC signal can, for DC, so this one is capacitor, so DC will go this way. But AC signal can go through this way. Because for AC signal, capacitor, it could be looks like a resistor. But for DC signal, the capacitor is like open. So DC signal cannot go through this one. So we call this free beam resonator. You apply AC signal, and the beam will vibrate. Just vibrate, like this one. And this is, say, metal one, say one metal layer. So if you put DC signal, you don't put AC signal, nothing will happen. The beam won't vibrate. In this case, you apply a force to pop to this beam. Apply force, and this force can go, say, AC force. The force, go up, down, up, down, up, down. If this is the AC force, then we have current output, AC current. Okay. Then, so this work is by Lee. Usually we will call the first author the major author. So this is this paper from Lee, and this is paper title, and this is the journal of Microelectromechanical Systems, and in the year of 2013. So when you tell someone your reference, the author name, the title of the paper, and the journal, and also the year of publication. These are the important information you need to give to your audience. Okay? Yes. Any good journal paper will need mathematical equations. So here comes the mathematical equations. Professor Yang always said, math. Without math, almost the value, you cannot sell your product in high price, low price. But some math will increase the price of your product. Okay, for this cantilever beam, it's a beam, so beam has a mass, and we have damping air damping, the surrounding air create the damping. And this is this is also a spring. So we have spring constant. So this is the force F applied to this B. So we have this mechanical model. But we can, for MEMS, people prefer electric circuit. They want to create the equivalent circuit model for the mechanical systems. Then MEMS is equivalent to inductance. C is equivalent to spring, mechanical spring. And so C is equivalent to resistor, and K is equivalent to capacitor. And force F is equivalent to voltage. Velocity is equivalent to current. So we can turn this model into an equivalent electric model. Okay, here it is. So C is the resistor, N is the inductor, K is the capacitor. But remember, capacitance equal to 1 over K. And F is the voltage, power supply voltage. And velocity is the current in the circuit. Okay, so this is the equivalent model for mechanical system. Then this is the circuit part. IN1, port 2. So this is port 2 for electric circuit. This is port 3. So IN1, the direction is just direction. You can say this is the direction, or R1. Don't fall asleep. R1. Why do we need what is this? What is this? What is the symbol in electric? Yeah, we have a resistor. So IA1 can go this way. You can assign IA1 this is positive direction, or you could say IM1 this is positive direction. It's up to you. So IM1 goes out, IM1 goes out, IM2 goes out, IM2 goes out. And this is the internal resistance. You say the wire connection, RINT, RINT. We have RINT, RINT. And this is piezo resistor. So piezo resistance. This is piezo resistance. And we need this current controlled current source. So this is current, IV is current in this mechanical system. This current will control AI is the gain of this current source. So AI, IV, this one is the current for this electrical counterpart. So AI is a coupling factor, the coupling between mechanical system and the electrical system, coupling factor. Then, okay, this is node B1, this is node B2. And we say IN piezo goes through this one. So this one is the piezo, AIIV. Also is IM piezo, the current in this range. Okay, then for this Pauli resistor, we have this equation. Delta R divided by R equal to pi L sigma L. But sigma L along this V in each component is different. So we need to do integration. So this is for each component, the distance is say dy. So we just add all small component together, but divided by total length to get the average value. So this is the average, pi L sigma L average value. Okay, so VD is the supply voltage divided by, this is the R, C, R times 1 is R, R times delta R divided by R is delta R. So this one is R plus delta R. So VD divided by R plus delta R is the DC, say ID, current ID equal to VD divided by total resistance. Then VD here, and R 1 plus delta R divided by R. Delta R divided by R is a small number compared to 1. So you could use Taylor series expansion. Taylor series expansion, you can do the fx equal to fx0 plus f prime x, x minus x0 plus f double prime divided by 2 times x minus x0 squared. Keep going. So this is Taylor's series expansion for polynomial. So if you do Taylor expansion for this one, so this one is fx equal to 1 plus delta divided by R, but we have minus first because this one is in the denominator. So you do Taylor expansion, you could get 1 minus delta R divided by R plus delta R divided by R squared minus delta R divided by R cubic. Keep going. But because delta R divided by R is very small, so we could ignore second order, third order, fourth order. We just keep this one. 1 minus delta R divided by R. And we say VD divided by original R is IO, the reference current. So, okay, this is how we get this equation. Okay, any questions so far? Did you, okay, can you? Where did you get this?
Mine.
Yours.
In Vietnam, from Vietnam.
Got this from Vietnam.
What a gift.
From Huế Tuấn.
No, my friend.
Okay. We have this mechanical system. And this is the VI, we can do equal to force, and IV equal to velocity. Okay. Then this is the electrical system. We got this one already. So from previous page, we have this one, this one. Now, here comes this equation. How did we get this one? I give you 1 minute to think about this. Okay, video. Camera up. Okay, so if you have derived this one, then we take this GM as the transconductance is the current divided by voltage. It's like the output current divided by the input voltage. We call this transconductance. So for the transconductance of the piezo element is the piezo element current divided by the voltage E. Voltage E is the force F. But F, we say F is equivalent to voltage. So if you IA piezo divided by V voltage, the voltage for the piezo resistor input voltage is the force. Then this one, say VI is the force, and piezo current here, this is IB. IB, we define IB equal to VD divided by original resistance. So IB here, delta R here, R here. So we got the transconductance for piezo resistor. Then from this equation, we divide each item by F. This one by F. So from this one, we get this one. So IN1, this is input force, VI. IN1 divided V for the transconductance for M1. And minus sign here. IM2 divided by F is the transconductance for M2, GM2. And this one is the transconductance of the piezo material. So we have this equation. Then we define GM1 minus GM2 is the differential transconductance. So GM1 minus GM2 is 2 GM1. So this is the differential transconductance. Okay, please continue this the derivation and derive each equation. Please, everyone. Good. So in this resonator, you see, if you apply AC force, you can have the AC current output. So it's a resonator. Okay, so this is a short introduction of the piezo resistive devices. So next we will go to, because the final device is a resonator, so we will use resonator as a filter. Usually we have RC filter, but electronic filter has low Q value. Mechanical filter has high Q value. Q is the quality factor. So let me open the PPT. Lecture 6 filter. Okay. Party B part. Party B part. Could you read the first?
Electronic filter, RC and RL single pole filters, multiple LC filters.
Thank you. For electronic circuits, we can use RC, RL, or multiple LC to create filters. Second one. Fortune.
So
solid state with a filter, operational amplifiers, OPA, and resistors.
Yeah, we can use OP and resistors to create filters too. But the third one is what we are going to discuss today. Leo, could you read the third?
Mechanical filter signals in the form of current or voltage are converted by an input electromechanical transducer into mechanical vibrations and the filter pass through the series filter and are then converted back into electrical signals by an output electromechanical transducer.
Okay, transducer, electromechanical transducer. Transducer is converter. In electric world, we have electronic, we have analog digital converter. But in mechanical world, we have electromechanical converter. So this electromechanical converter, electromechanical transducer. Transducer is similar to converter, energy converter from different types of energy. So electromechanical means, say we input electrical energy, we can have mechanical energy output. It can be used as a filter. So electrical signal in, then electrical signal out. And this is the mechanical filter. For high pass filter, low pass filter, or band pass filter, the same. Okay. Your friend disappeared. Kumel, could you read this?
For functions where solid-state transistors are inadequate, discrete and bulky ceramic components are utilized, thus restricting the achievable level of system miniaturization.
Okay. Sometimes mechanical resonator, we have the ceramic. So if you have a watch, we need the ceramic, piezoelectric ceramic transducer, oscillator, to drive the watch, yeah, inside your watch. We have oscillator, mechanical oscillator, but it's very bulky, means large, bulky. So it's not good, and it's a discrete component. Discrete is, say, bulky, large, and power consumption huge. So it's not good for miniaturization. Kaiser, could you read this?
Miniaturization.
Okay. And also electronic filters, low Q value. Okay. And before we continue, we will introduce you the two-pole S parameters, because we need them in our discussion. So this is a two-pole system. So port 1, port 2, and port 1 we have incident A1, reflected B1. So if I ask you to walk through this wall, probably it's going to hit hard. But if it is just vacuum, so you could just walk through it. For the material between vacuum and the solid wall, some part of hue could walk through it. Some part of hue will be reflected back. Different media has different properties. So for each medium, some signal will go through, some signal will be reflected. This is natural. So, okay, this is port 1 and port 2 the same. Some signal gets in, some signal got reflected. So, okay, so this is the two-port system. We need the mathematical equation to calculate the percentage of transmission and the percentage of reflection. Okay, say B1, B2 on the left-hand side, A1, A2 on the right-hand side. Because A1, A2 incident, B1, B2 reflected. So between, this is 2 by 1 vector, this is 2 by 1 vector. So this metric must be 2 by 2 because 2 by 2 multiplied by 2 by 1. The result is 2 by 1. Dimension should be compatible. N multiplied by NQ. The result is NQ matrix. NQ. The result is NQ matrix. So 2, 2, 2, 1. Result is 2, 1. Either 3, 4, 4, 2. What's the result of the matrix dimension?
2, 2.
Again, 4, 3, 3, 2. The result is the dimension of the resulted matrix. 4 by 3, 3 by 2.
2 by 1. 2, 1.
4 by 2, 2 by 1. 4 by 2, 2 by 1. What's the dimension of the resulted vector? Kumel? Yeah, 4, 1. Okay, so S11 equal to, say, B1. B1 equal to S11 A1 plus S12 A2. But S11 is when A2 is 0. If A2 is 0, we just consider this one. We don't consider the other side. We just put a signal in and measure the output signal. Just one port measurement. For one port measurement, there's no A2. So B1 equal to S11 A1. B1 equal to S11 A1. So this is under the condition. We don't consider port 2, just one port. So S21 the same. S21 equal to B2 equal to S21 times A1 plus S22 times A2. But this one, under the condition A2 is 0. So we just consider A1 in. We measure signal in and signal out. There's no A2. A2 is 0. So B2 divided by A1 is S21. So we can just figure out. So R1. So under which condition S12 equal to B1 divided by A2? What? Under which condition? S12 equal to B1 divided by A2. I mean, V1 equal to S11A1 plus S12A2. Under which condition you can write V1 equal to S12A2? Why? Under which condition? Kumel?
During the reflective condition.
Huh? Watch it. V1 should be equal to S11A1 plus S12A2. Under which condition we can write V1 equal to S12A2? Here.
S11 equals 0.
In this system, we have two inputs only, A1 and A2. We have two inputs. Huh?
A1 0.
A1 0, S1 2.
Yeah, A1 equal to 0. Okay, so for this, S22 equal to B2 divided by A2. So under which condition we can write down this solution? Like, here.
A1 0.
Yes. Under the condition when A1 is 0, we can write B2 equal to S22A2 because B2 should be equal to S21A1 plus S22A2. But if you just write this one, means B2 equal to A2, S22A2 only. So what happened to this term? It must be 0. Okay?
So if A1 0, so S11 will be infinity.
No.
Yes.
No. This is electrical two-pole system.
No.
S11, S12, S22, S12, they are the system parameters. System parameter means it's a machine. It's a machine, you cannot change anything. But you can change the input to the machine. To this machine, we have only two inputs, A1, A2. So either A1, 0, A2, 0, or A1, A2, 0. B1, B2 are output, input A1, A2, output B1, B2. S11, S12, S21, S22 are the machine. The machine or the motor, compressor, engine. When you buy the machine, it's the machine. You cannot change anything. The only thing you can change is you can change the engine or you can put the oil inside, engine oil, gasoline or electricity. Okay?
I'm talking about the mathematics.
We are talking about this two-pole system. Okay? Then inversion loss. See, we have power in, power out. We have transmission line. Transmission line. So we have input to the output. You can imagine you have a cable, you have wire. But if you cut the wire, you put a switch between the input and output. So this switch, it has resistance, it has inductance, it may have capacitance between this switch to the ground. So after you put this switch between the input and output, you have energy loss. So if we say PT is the power to the load, from power, this is your load, this is your power. From power to load, we have power PT. But after you insert something, some component between the power and your load, then the power is going to decrease during this something we put. So this is PR is the power to the load. after you insert some component there, say filter in this case. So we have one metric to calculate the loss. If you insert something between power and load. So we use this insertion loss IL, but we use decibel to compare PT to divided by PR. So 10 log 10. But sometimes we use, because power equal to V squared divided by R. So power equal to V squared divided by R. Power equal to V squared divided by R cancel out. So we can write V1 squared, V2 squared. If we move the square in front of the log signal, so this is 20 log V1, V2. So don't be confused. If we use power, this is 10 log 10. 10 is the base. If you use voltage, this is 20 log 10. Ethan, do you understand? Leo. Okay, insertion loss. So dB positive means PT larger than PR. If okay. So okay, for filter, if this is a band, like we have low pass, we have high pass, we have band pass filter. For high pass filter, it should go this way. At low frequency, no output. At high frequency, we have output. For low pass filter, low frequency signal, we have output. The high frequency signal, we don't have output. But for band pass filter, means at certain band, the signal can go through. Outside this band, signal cannot go through. So this is the band pass filter. From frequency F1 to frequency FL to F high. Between this range, signal can go through. So this is band pass filter. And usually, so this is the peak amplitude. And if this is the reference, 3 dB, minus 3 dB, from this magnitude to minus 3 dB, you get 0.1 and 0.2. So you draw a vertical line to this frequency axis. You draw another vertical line to this frequency axis. You can get frequency FL and FH. So this is the definition how to get the frequency, low frequency and high frequency. You use the 3 dB level. From 0 dB, you lower to 3 dB, you intersect 2 points of this frequency response curve. So use these 2 points, we can get FL and FH. Okay, Leo, do you follow me? So this is the bandwidth. So this is the method to calculate bandwidth. Kaiser, could you read the first point?
The absolute bandwidth divided by center frequency.
Okay, so this is the bandwidth. The bandwidth B divided by the center frequency, MO, is the fractional bandwidth. Because frequency world, we have megahertz frequency, we have gigahertz frequency, we have, say, kHz frequency. But if you say, okay, the bandwidth is 100 hertz, it doesn't make sense because you need to consider what's the frequency range in megahertz range or in gigahertz range. So that's the reason the bandwidth should be divided by the center frequency. Then we can compare gigahertz or megahertz. So in gigahertz, suppose we should have large bandwidth, but megahertz we should have smaller bandwidth because it's in the megahertz range. So you want to compare these two different world signal, you need to divide it by their center frequency to be fair comparison. So if you can run, say, your speed in 100 meter race, you take 10 seconds. But for a children, 6-year-old, it takes 20 seconds. But you cannot compare these two. You need to divide it by your age. So normalize. You can compare these two speed. Bipa, could you read the second point?
The center frequency is usually defined as the arithmetic mean of the upper and lower frequencies.
Okay, mean is the average mean, and arithmetic mean means we have a lot of ways to calculate average. You can say FL squared plus FH squared divided by 2. This is one definition of the average. But you can say FL cubic plus FH cubic divided by 3 is the average. You have different definitions. Arithmetic mean means linear mean, means FL plus FH divided by 2. This is arithmetic mean. Kyler, what is arithmetic mean?
A plus B divided by 2.
Okay, easy, right? Then let's see what time it is. 3:44. For piezoelectric material, if you input AC power, it will generate AC vibration. So it has the electromechanical conversion power, piezoelectric material. And we have a metric or a number, a measure, KT squared is the ratio between mechanical energy divided by electrical energy. Because electrical energy is, we have some energy loss, then we can have mechanical energy output. So the output energy, mechanical energy divided by the input energy, electrical energy, is the electromechanical coupling coefficient. So for piezoelectric material, so E33, epsilon 33, C33, they are all the material properties of piezoelectric material. Okay, so for the derivations of that, you could go to kt2.pdf, page 37. If you go to iLearning, go to lecture 6, kt2 PDF. So it's a book for weather lectures by, so if you go to page 26, 36, 26, you will find how to derive the KT squared. And for this equation, it's on page 65 of this book. This is the electromechanical coupling coefficient. Then also from this journal paper, we also have this equation. Okay, so if you are interested, you could go through those books and the journal paper. Okay, so now we are going to officially to discuss the resonators. Now we have some background knowledge. Okay, so previous slide, PPT, we have Journal of Electromechanical System. That's the #1 journal in MEMS. And the #2 journal in MEMS is this one, JNN. That one is JMEMS, and this one is #2 journal. Journal of Micro Mechanics and Micro Engineering, JNN. The #2 journal, JNN. So 201, page 70 to 80. The first author, R. So, okay, he wrote this, published this journal paper about the resonator, capacitive resonator. Okay, this is for every presentation. First is the schematic and the operational principle. Always, you need to let your audience know what you are talking about. So schematic is the very good communication tool to give people at least have some image about your device. Okay, his device is a beam. We have anchor 1, anchor 2. This beam is ground. For this anchor 1, we have voltage DC and AC, voltage E. For anchor 2, peg 2, we have AC voltage, DC voltage and AC voltage. And you can think we have capacitor 1, gap GU. This is capacitor 2, gap GL. So U, okay, Kumel, why the author selected the subscript U? No idea. Like, why he used U as a subscript?
Maybe the change.
U and O.
It's L. It's L.
U and O. So why he used U here and L here? Anyone? Yeah. Right. Upper and lower. So when you create your schematic, for all this, G stands for what? Why he used G? Yes, gap, G. So in academic world, don't invent any symbol. So if you use this name, it must have some meaning. Why we use it? We don't use A, we don't use B, we don't use C. C is for capacitors, and G is for gap. So don't use L here. If you use L here, very possible your paper will be rejected, because if they look at this, this must be a no experience, low level paper. They even don't want to spend time to look at it. So the page 1 is very important. Your figure 1 schematic. If you draw a very beautiful schematic, and when people look at your schematic, probably they know everything about this paper. If your figure 1 schematic cannot give people the very good idea, then probably you will fail. So this is the reality. So schematic figure 1, very important. See figure 1. And all the names carry some meaning with it. Upper gap, lower gap. So B, and the coordinate system. So this is the positive direction of your x coordinate. It's very important to have an arrow here. Some low-level authors, they just say, okay, this is x. They don't put an arrow here. Then we don't know which direction is the positive direction of your x coordinate. So it's also important. And for electrical, we all know the upper case for DC, the lower case for AC. So for mechanical engineer, you need to have this common sense. Okay, then, so this is the mechanical system. And this is the electrical system. We have two ports, port 1, port 2. This is port 1, this is port 2. So this one is this electromechanical system. It's a black box. Then voltage, so this is ground, so you can say this is ground, this is positive. So the voltage VSO plus VS, the voltage VDO plus VD, and the current ID, current IS. So this arrow direction is arrow head is also important. Means this is a positive value for IS. And if you go this way, means IS is negative. So the arrow head is important in your schematic. Now, equation, MEMS is also important. A journal paper without equations, probably you will fail. This is the reality. People don't want just simulation. People want theory, equation, mathematics. You want to produce high-level paper, mathematics. If you want to produce low-level, low-value paper, simulation. You got it. Okay. Okay, then we have two capacitors. Capacitor 1, ID. Why we have ID? Because we have QT, the charge on the electrode. If the charge is a function of time, means you have current. Because dq dt is a current. And the Q is the charge. Charge equal to C times V. C is the capacitance, V is the voltage, the potential between the two electrodes. So if Q equal to C times V, C times V, then we can do one thing. QD equal to CD is the capacitance times V. So this is ground, and V is VDO plus VD. So dq dt, dq dt. So we have two items. Do the differentiation means we should do this. The first item, dc dt, and we write down the second item, VDO plus VD. Then plus, now the first item is the constant. Then the second item is VDT. VDO plus VD. But you see this one, they just keep the VD here because, see, this one, VDO, okay, let's take a look at this one. VDO is DC differentiation, constant differentiation, so this one will disappear. So that's why we have this one here, and this one is this one. Leo, do you understand? The same for IS equal to QS dt, and QS equal to CS times VSO plus VS. So you do the same thing, you can get equation 2. Heather, would you read this?
Where ID is the current through the
Stop. If you read this one, IT, so you should read this way. ID of T. ID of T means ID is a function, T is a variable. So ID is a function of, ID is a function of T is time, but it's too many words. So we just say ID of, we just ignore it. Ignore it. We just say ID of T for simple. Okay. Again.
where ID of T is the current through the upper capacitor and IS of T is the current through the lower capacitor.
Good. Okay. Now, we have some assumption. This is the DC signal. So, VDO is the DC for the upper capacitor. VSO is the DC for the lower capacitor. And VD is the AC for the upper capacitor. VS is the AC for the lower capacitor. VD and VS are much smaller than VDO and SO. Also, we assume, Deepa, you are sleepy. We also assume VDO minus VSO. VDO and VSO are not close. They separated certain distance from each other. So this one minus this one is also larger than this one and this one. And we just give a name to the DC differential. The DC differential VDC equal to VDO minus VSO, much larger. If you just have one, means larger. If you have two, means much larger. Okay, so under this condition, we can simplify 1 and 2 to 3 and 4. So we will continue this next Tuesday.